Hello, and welcome to my paper presentation of Error Handling of In-Vehicle Networks Makes Them Vulnerable, originally written by Kyung-Tak Cho and Kang Ji Shin, and I apologize if I am mispronouncing their names. So just heading into a bit of introduction before we get started, the authors are once again listed here, and they were originally from the University of Michigan and published this paper in 2016 at the Conference on Computer and Communications Security. Also, the link to the paper is listed here on this slide, but I will be sure to include it in the description of this YouTube video. So the motivation behind this paper was really to talk about security and privacy, as well as system security, as we all know is a very important topic to discuss, and also to introduce a new denial of service attack. So the approach that the authors and myself will take in explanation of this paper is to first introduce the idea of control area networks, or CANs, which is an abbreviation which will come up many times during this presentation, and then introduce the bus off attack, which is the denial of service attack that the authors introduce and create, and then talk a little bit about the feasibility of this attack in real world scenarios, and finally propose some solutions to this problem. So just as an overview going into this presentation, some points to keep in mind are electronic control units, or ECUs, onboard vehicles make them susceptible to modern-day security attacks. One such denial of service attack exploits the error handling scheme of in-vehicle networks, or control area networks, or CANs, hence the name bus off attack, which will make more sense as we go through the presentation. Then we will talk a little bit more about some analysis, real-world example, and proof of practicality, and then suggest possible solutions, some discussion, and the conclusion. Thus, creating the problem statement, how can we better secure in-vehicle networks? So just going throughout this presentation, just try to keep that in your mind of how can we better secure the networks inside of the vehicles and protect the computers on board the vehicle. So starting off, control area networks. What is a control area network? Well, a control area network is essentially a connection of nodes on a vehicle's internal computer network. And each node periodically broadcasts data frames onto the bus topology. And for those who might not know or might need a reminder, there is a picture of a typical bus topology on the bottom there. So for instance, let's assume the top left computer or node decides to send a message onto the bus. That means that the three other nodes on that bus will also have access to that message that's being sent. Also, that means that if two computers or two nodes were to send a message at the same time, there would be a collision, meaning that there needs to be some sort of scheme or protocol that will control this and make sure that there aren't too many nodes sending messages at the same time. Moving on, each frame is a sequence of dominant 0 or and recessive bits, where dominant is a 0 bit and recessive is a 1 bit. And the reason for this is because the bus basically operates as a logical AND gate. And so when you AND together a 0 and a 1, the 0 is what ends up staying. Hence why the authors chose to go with the scheme of 0 being the dominant and 1 being the recessive bit. And lastly, instead of a sender or receiver address, much like other communication methods and protocols, the CAN frames contain a unique ID representing the priority and meaning. And more importantly, that implies that there's only one ID per ECU. Also, consecutive frames are separated by a 3-bit interframe space, or IFS. And it's also worth pointing out that each manufacturer typically implements their own security for the CAN bus by having their own cyclic redundancy check, or CRC. But then the question comes up to be, what if two nodes or two ECUs have a message that they both think is important that they want to send at the same exact time? That's where arbitration comes in. So once the CAN bus is detected idle, A node with data that needs to transmit something starts a frame transmission by issuing a start of frame, or SOF, which is what you see on the left side of the screen. Then, during transmission, each node sends its frame one bit at a time and monitors the actual output that comes on the CAN bus, which is why we have in this image node A, node B, and on the bottom the actual CAN bus output. So as an example, let's assume that node A be some data being sent by an ECU somewhere that has the wheel speed, and let node B be the battery temperature. So here we see node A and node B have the same first few bits, but in the middle, we see that node B has a 1, whereas node A has a 0. When those two are ANDed together, the 0 bit is going to be what remains, and hence node B, looking at the CAN bus at the bottom, sees that his, or the computer's 1 bit that's sent actually came out to be a 0, meaning that there's another ECU, another node that's trying to send data. That signifies to the node B that it's not their appropriate turn to send data, and they go into receiving mode instead of sending mode. And node A continues sending the message. So, as you can probably imagine, there does need to be some sort of way to handle errors. And this the CAN bus protocol has 5 exact ways for handling errors. So the first one is bit error. And this happens in a situation where how every transmitter who's transmitting some data in the frame compares its transmitted bit with the output bit on the CAN bus. And if the two are different, there's a bit error that occurred, except during arbitration. So going back to this example real quick, if node A and node B were to have this issue outside of arbitration, node B would have suffered from a bit error. But since it's during arbitration, there's no error flag raised. Moving on, a stuff error happens after every 5 consecutive bits of the same polarity. So when there's 5 0 bits or 5 1 bits sent in a row, an opposite polarity bit is stuffed in order to maintain soft synchronization, which is something that the frame and the protocol requires. And violation of this incurs a stuff error. And then CRC, form, and acknowledgement error are all very similar in the sense that they have to do with the formatting and packaging and organization of the frame. But very quickly, CRC is a cyclic redundancy check error, which essentially says that if the calculated CRC is different than the received CRC in the frame, there's an error. Similarly, the form error is when there is something wrong with the frame, such as the CRC or the IFS is different than what's expected. And the acknowledgement error is when a node transmits a message. Any node that has received it issues a dominant or 0 bit in the acknowledgement slot, and if not, then there's an acknowledgement error that is raised. Okay, and additionally, there's also 2 error counters. There is the transmit error counter, or the TEC counter, as I'll probably refer to it. There's also the receive error counter, or the rec counter. And there are lots of situations that can alter these counters, but most importantly, a node that detects an error during transmission increases the TEC counter, or the transmit error counter, by 8, whereas if perceived during reception, the rec counter, or the received error counter, is incremented by 1. Additionally, for any error-free transmission or reception, the TEC and the rec are decreased by 1, respectively. So if there's a successful transmission, the TEC is decreased by 1, and if there's a successful reception, the rec counter is decreased by 1. Cool? So here we have the CAN's fault confinement scheme. Notice how there are 3 different states, and on the top left we have the error active, which is what every ECU or every computer or every node on the CAN starts in. And if the TEC or the rec counter, so either of the 2 error counters, reach a value of above 127, the node would switch over into error passive mode. And from there, if the tech ever reaches above 255, then it would reach a bus off mode, which essentially forces where the CAN protocol forces the computer or the ECU or the node to turn off, essentially kicking it off of the bus altogether. Also, it's worth pointing out that it is possible for a node that has entered error passive mode to go back to error active mode if the tech and the rec counters are below 127 or equal to 127. All right. So just a quick recap on CANs and control area networks. So what is it again? It's a bus topology of vehicle ECUs. And if one node has or is accused of too many errors, it will be forced off eventually if there's, 255 plus errors. And CAN frames don't have addresses, but rather IDs to indicate priority and meaning. So this lets us lead directly into the attack scenario, but before that, let's discuss two assumptions. The first assumption is that the adversary can somehow gain access to the CAN, either remotely or physically. The reason this assumption needs to be made is because the authors have outlined in their paper that there are numerous other resources, other articles, and presentations discussing how it is possible for an adversary or an attacker to gain access to a computer's network. But for this specific denial of service attack, the bus off attack, it's going to be assumed that the attacker and adversary already has access. Additionally, assuming that the attacker has access to the network, we also need to assume the adversary can inject and sniff any messages on the CAN bus. And this is necessary because the attacker, the ECU that's a part of this network, this CAN network, needs to be able to not only see what's the other nodes are sending, but also send messages for this attack to work. Cool. So from a high level, the attack overview is essentially pretty straightforward. By iteratively injecting attack messages, an adversary or attacker can cause an uncompromised or otherwise healthy ECU to increment their transmit error counter all the way up to 255 plus, causing that healthy ECU to turn off. Pretty simple and straightforward. However, there are three conditions for this attack to be considered successful. The first one has to do with the ID. The adversary frame must have the same exact ID as the victim node's message. The second condition is the timing. The adversary must transmit the frame at the same exact time as the victim node normally does. And the third condition to be met is content. So the content has to be exactly the same up until the actual exploit is triggered. So what that means is there needs to be at least one bit position with a dominant, and again, that's a 0 bit, where the victim's message has a recessive, or 1 bit. And every bit prior to that must be the same in both messages. And that too must occur after the arbitration period. And I'll show you what that means in just a moment. So in this example, we have the victim V at the top, adversary A in the middle, and the actual output on the CAN bus at the bottom. So notice how the arbitration period is exactly the same. The adversary is sending the same bits at the same time. Thus, the CAN bus is putting out the one message that applies to both the victim and the adversary. So both nodes think that they are in control and that their message is winning. And after the arbitration period is over, the victim is like, oh, okay, well, I guess it's my message because that's what I see on the bus. However, at the point where the victim has a 1 in their frame, the adversary puts a 0, and that's where there's the red bar on the image. And because of that, the victim says, oh no, there must be another message that's more important, or something happened because the bit that I was supposed to send, which is a 1, is not on the CAN bus. And so that makes the victim go from sending mode to receiving mode, and also increments their tech counter by 8. And as soon as that happens, the adversary then triggers a stuff fault to cause an error on the bus itself. And after that happens, the CAN protocol has a feature which allows both parties, or I guess the failing node to retry sending that packet or that frame. All right. So that's pretty much an overview of how the attack happens. But there are two phases to this attack. The first phase is when the victim is in error active mode. So remember, error active is where all the nodes start. That's the top left blue one. But with just one message, the adversary can send the victim and itself into error passive. And that too is a little bit confusing. So what happens is after the first message is sent, the victim has its tech counter increased by 8. And because of the stuff error, the adversary also has its tech counter incremented by 8. But because of a feature that allows the frame to be sent again for for retrying purposes, both the adversary and the victim will try to send the same exact frame once again at the same time. And so it makes it very simple for the adversary to increment the tech counter of the victim pretty much exponentially, like super quickly. And phase 2 now is when the victim is in error passive mode. So what'll happen is after the victim goes into error passive mode, meaning that its tech counter reaches above 127, the victim will still be sending bits onto the bus. And so instead of forcing that stuff error, as we see in the last slide, so instead of forcing that stuff error by sending 5 ones in a row, it'll just send a normal message until it's finished. That way, it'll reduce its tech counter by 1, which will keep it in error active mode and keep it from going to error passive. So in phase 2, the victim is in error passive and the adversary is in error active. And after that, the adversary can still iteratively send messages at the same scheduled time as the victim, causing the victim's tech counter to eventually increase to 255 plus, causing it to be forced off and kicked off the bus. But if we're thinking about this, how feasible is it really? Because what if the contents of the frames are different, or if the IDs aren't the same? And most importantly, the time synchronization, how can that really be achieved? So this introduces the idea of preceded IDs. Nodes that have either lost arbitration or have a new message buffered while the bus is busy attempts to transmit the message as soon as the bus becomes idle. Thus, a preceded ID is defined as the ID of the message that has completed its transmission right before the victim tries to send its message. But that then brings in the question that we need to consider: do preceded IDs even exist? And if they do exist, how many of them are really unique? And if that, is there a pattern that the attacker can use to take advantage of the situation? So if we look at this graph on the right, we'll see that this is the graph this graph has data that was generated based off of a 30-minute test drive of a 2010 Toyota Camry. And this data shows that there were 42 distinct messages transmitted. And specifically, it shows the number of distinct preceded IDs of the ones labeled on the x-axis, and all of that is in hex. So for example, 20, 23, 223, 3B7, etc. So for instance, the message shows that B2 had a unique preceded ID of B0, and B2 always followed B0, where both were sent every 10 milliseconds. However, on the other hand, message such as 3B7 had 11 different kinds of preceded IDs. The results showing that 10% of the periodic messages have a unique preceded ID answers the question of whether this is possible, whether they exist, if they're unique, and if there's a pattern, thus implying that the bus-off attack can most definitely exploit genuine preceded IDs, and it is indeed feasible on real-life cars. It's also worth noting that preceded IDs can also be fabricated through the use of complex but established and tested formulas following Gaussian distributions to calculate the jitter in the bus topology, but that's beyond the scope of this presentation. So here we have two graphs for the CAN prototype test. On the left, we have a graph that shows the transmit error count of a victim's tech and an adversary's tech, or the transmission error counter. Notice how it increases to about 127 almost immediately or exponentially in phase one. And in phase two, you can see that the tech of the adversary declines steadily as it sends good messages and reduces its count by one. Whereas in phase two, it also increases pretty steadily, but at a slower rate. And on the right side, we have the transmit error count of the victim. It's important to notice that they both look the same and increasing at the same rate. However, notice the x-axis that in phase one, the victim increases its tech in about 2 milliseconds, whereas phase two, it took much longer. Additionally, these two box plots show the attack under different bus conditions, and as it should be, the error passive mode was reached much quicker when the CAN bus speed was faster. Similarly, the bus off attack itself occurred much quicker when the bus speed was faster. And this makes sense because if a bus is operating at a faster speed, and by that I mean the transmissions are happening quicker, then the victim has more opportunities to retry and try to send their messages after it reaches error passive mode, thus allowing the adversary to also step in and trigger the attack and take advantage of the vulnerability just as quick. So revisiting the attack conditions, we have three things that we need to consider. First, which is the ID. We need to make sure the adversary has the same ID as the victim. The same timing, which we can solve using periodicity, which is the complex math to estimate timing, but also preceded IDs. And within that, you can use the genuine ID by having the attacker observe and wait, but you can also fabricate the ID. And then also the content. Specifically, let's talk about periodicity versus preceded ID, since timing is the most difficult part of this vulnerability. So periodicity, only 58 out of the 50,000 trials succeeded in causing a bus-off attack, meaning that 0.12% succeeded, whereas the attacks that used genuine preceded IDs had 100% success in all 50,000 trials. Similarly, the fabricated preceded IDs had 45,127 out of 50,000 trials succeed for a rate of 90.25% success, which is awesome. So now transitioning into real life examples. So the authors decided to use a 2013 Honda Accord to try and show the feasibility and practicality of this vulnerability. Notice how they had access to the OBD2 sensor or the computer that way, and they had 3 ECUs or different machines that they inserted into the CAN on their prototype. So what they did was they tried to use one of their machines that they introduced into this CAN topology to trigger an attack on one of the existing ECUs. However, because of security reasons, they weren't able to actually find the specific tech counters of the onboard computers. And so this graph on the right shows the attacker's transmit error count, which, as we all know, should be equivalent at least in phase one. So they launched the attack 15 times, and 13 of those 15 times we can see that the attacker's tech count went above 127, meaning that the onboard computers were taken into error passive mode at least 13 of the 15 times, if not completely entering bus off mode, Additionally, they chose to test on a 2016 Hyundai Sonata with a similar 3 computers that they introduced onto the CAN bus. And similarly, they launched 15 tests, but only 1 failed this time. And as you can see from the graph, 14 of the 15 times, the attacker's transmit error count reached above 127, implying that the actual onboard ECU that was being attacked also reached a tech count of above 127. But not only did they do that, they also decided to launch an attack onto the other prototype. So going back and explaining this, notice how there's three computers or devices on the prototype. So one is they used to launch an attack onto an existing ECU, but by connecting all three of those to the computer, it essentially introduced those two nodes or those three additional nodes into the entire network. And so since they were successfully added to the in-network CAN network, they were operating and acting as if it was a real ECU. And as a result, an attack on one of those is synonymous and equivalent to an attack on a real ECU. However, it's important to point out that their attack was a lot more difficult and it was different than the prototype testing, especially because the CAN bus on a real vehicle was much more hectic and difficult to predict. As you can see here, the red line is a 2016 Hyundai Sonata, and the dotted blue line is a 2013 Honda Accord, And though it is different because of the more complex CAN bus traffic, the general curvature was the same as what the prototype showed, where we can see that phase 1 finished incredibly quickly, and phase 2 still finished, although not as steep and predictable as one would assume, but still eventually reaching to the eventual 255 counter, causing the ECU to go into bus off mode. So the authors also suggested some possible countermeasures. So one countermeasure has to be taken account in phase 1 and the other in phase 2. And a combination of these 2 points is how to flag and take note of a bus off attack. So the first one is in phase 1, you have to keep a lookout for at least 2 consecutive errors that occur during the transmission of frames. Thus, whatever new mechanism should watch out for consecutive error frames with an active error flag. And in phase 2, at the time when the error passive victim's tech counter increases, a message with the same ID will be successfully transmitted by another ECU. Another potential countermeasure that was discussed is instead of looking at consecutive error frames, look at consecutive errors that occur in the same bit position. However, it was decided that this would be far too expensive computationally and financially, since it would need to apply to all different sorts of car manufacturers that put ECUs in their vehicle instead of a small update to the CAN bus protocol. So just as a discussion, high level, the dangers of the bus off attack are definitely that it doesn't require anything complex, especially something such as reverse engineering. Much like other attacks that are much more involved, it is considerably easier to mount the attack and actually have it done. And all it takes is one correct timed attack from the adversary, and the victim already basically automatically enters phase 2, since the CAN bus has a retry feature built in. However, two of the limitations of this attack scenario is that the attacker must successfully synchronize the transmission time, which is actually incredibly difficult. And this also assumes that the adversary already has access to the control area network. So as a conclusion, just wanted to recap everything we've discussed. This new vulnerability is called the bus off attack, is a denial of service attack that disrupts one, if not more, ECUs on board a vehicle. And this can be something small, such as the AC or battery temperature ECU being not responding and kicked off the bus, but it could also be much more difficult and dangerous of a task. This vulnerability exploits the error handling scheme that is built in to the CAN bus protocol, especially since the retry functionality is there to help frames get passed correctly, and it exploits that very scheme. And we also analyzed the practicality using a prototype and 2 real cars, the Honda Accord and Hyundai Sonata. And we also discussed a possible solution that would be possible and feasible to implement. And these are my sources. Thank you.